Ever feel like your brain is just juggling a million facts, trying to connect them all without, dropping anything important?
Oh, absolutely. It's a constant challenge for us humans efficiently learning, remembering huge amounts of information.
Seeing the links.
Yeah,
Things that might not even seem related at first.
exactly. It's fundamental to how we make sense of the world, really. Our minds are, well, incredibly adept at taking in new stuff and fitting it into what we already know.
Right, that dynamic interplay.
Yeah, that allows us to navigate complexity, solve problems.
And that's exactly where our deep dive takes us today. We're looking at how the cutting edge of AI research is tackling a similar challenge.
Uh-huh.
How to equip machines, you know, large language models, with the ability to continuously learn and integrate new knowledge without just getting overwhelmed.
And the research we're looking at today is really fascinating. It's a novel way to enhance the long-term memory of LLMs.
Those powerful AI systems that are, let's face it, rapidly changing how we interact with tech.
What's particularly exciting here, I think, is the direct inspiration from our own minds.
Right.
We're talking about a new retrieval framework designed to give LLMs a much more nuanced and effective way to absorb and connect new information over time.
Think about the implications for a moment. As these AI models evolve, their capacity to retain and link information long term, that's going to be paramount.
Definitely. Whether it's a scientist tracking breakthroughs or a lawyer synthesizing case law.
Or a doctor integrating the latest medical findings, yeah.
Mhm.
The demand for efficient knowledge management is just enormous.
Mhm.
And that's where our focus lies today. We're diving into something called HIPPO.
HIPPO. Yeah, the name itself kind of gives a clue, doesn't it?
It does.
It's a neurobiologically inspired retrieval framework for LLMs built specifically for, well, deeper and more efficient knowledge integration. And like you said, it draws principles from the hippocampus and the neocortex.
Key brain regions for memory.
Exactly, essential for how we form and recall memories.
All right, so our mission today, unpack HIPPO. Understand what makes it pick.
How it works, why it's potentially a big deal.
Yeah, and the broader implications, right, for AI, for how we handle information itself. So let's start with the blueprint, the human brain. What specific aspects of our memory sparked this?
Well, the researchers really looked closely at the hippocampal indexing theory of human long-term memory.
Okay.
This theory suggests our long-term memory isn't just like one thing. It's more of a collaboration between different brain regions. And the theory really emphasizes two key functions: pattern separation and pattern completion.
Pattern separation and pattern completion. Okay, let's break those down. What do they mean, like in our daily brain operation?
Sure. So pattern separation is basically our brain's knack for creating distinct, unique representations for different experiences, even if they're pretty similar.
So we don't get memories all jumbled up.
Exactly. Think about where you parked your car today versus last week. Even if it was the same spot, your brain makes separate patterns for each time. And pattern completion, that's the amazing ability to retrieve a whole memory, even from just a small piece, a fragment or a cue.
Like hearing the first few notes of a song.
Yeah, and suddenly the whole melody, maybe even feelings associated with it, flood back. That's pattern completion.
Makes perfect sense.
Yeah.
So how do these two functions relate to those brain areas you mentioned? The neocortex, hippocampus?
Right. So the theory highlights three main players. First, the neocortex that processes the initial sensory info, the data we encounter, kind of the main processing hub.
Okay.
Second, the parahippocampal regions. Think of them as connectors, bridging the gap between the neocortex and the third component, the hippocampus itself.
The index.
Exactly. The hippocampus is theorized to act like an index. It rapidly forms connections between the different elements of an experience processed by the neocortex. And that index is what makes pattern separation and completion possible.
Interesting. So the hippocampus doesn't store the detailed info itself, but creates a kind of map, an index to retrieve details from the neocortex later.
That's the core idea, yeah. The hippocampus creates these sparse, interconnected representations, these indices, binding together the detailed info stored across the neocortex. When you try to recall something, a partial cue can reactivate this hippocampal index.
And that pulls the full memory pattern from the neocortex.
Precisely.
Okay, fascinating peek into our own memory.
Yeah.
Now, let's connect this back to AI. How does this biological inspiration help with the shortcomings of current AI memory systems, specifically something called RAG?
Right. This is where the connection gets really clear. The paper focuses on retrieval augmented generation, or RAG. It's a super common technique now.
Yeah, I've heard a lot about RAG.
It enhances LLMs by letting them pull info from external sources, like a huge database of documents, right? And use that retrieved info to generate better, more relevant responses, like giving the LLM its own research library.
Right, so it's not stuck with just its training data. It can grab relevant stuff in real time. Sounds useful. So where does it fall short for long-term memory, connecting different knowledge pieces?
Well, the main challenge with standard ARGA is that it often struggles to integrate new knowledge that's spread across multiple different documents or passages.
Ah,
Each new piece of info is typically processed and coded kind of in isolation. There isn't a strong mechanism to link it automatically to related info elsewhere.
can you give us a concrete example? Make it really clear.
Yeah, the paper has a great one in Figure 1. Imagine trying to find a Stanford professor who also works on the neuroscience of Alzheimer's.
Okay.
You've got this huge pile of documents, maybe thousands of Stanford profs described, loads of different Alzheimer's researchers. Standard ARG, because it treats each document separately, would probably only find the professor if one single document explicitly mentions both Stanford professor and neuroscience of Alzheimer's.
So if one doc mentions Professor Smith at Stanford, and a different doc talks about Smith's Alzheimer's research, Standard Ag might just miss that connection entirely.
Exactly. Unless there's one self-contained bit linking both facts directly, the system could struggle. But we humans, if we know Professor Smith, we'd likely make that connection instantly,
Yes.
right?
Yeah, absolutely.
Our brains excel at forming those kinds of associations. And the paper points out many real-world tasks need this, like reviewing scientific literature, prepping a legal brief connecting different precedents.
Or a medical diagnosis, pulling findings from various studies.
Precisely. It requires this cross-passage knowledge integration. It's not just finding isolated facts, it's about synthesizing information, drawing connections.
So how do current RE systems try to handle this?
Well, they often have to rely on iterative retrieval.
Iterative, like multiple rounds.
Yeah, multiple rounds of searching and processing, trying to piece together the relevant info bit by bit. But that can be really inefficient.
Slow and costly, I imagine.
Right, takes more time, uses more compute. And even then, it might not be enough for really complex integration, especially for what the paper calls pathfinding multi-hop questions.
Pathfinding multi-hop questions. Okay, that sounds like a key hurdle. What makes those so tough?
These are questions where the answer isn't just one direct link away. There might be multiple possible connections between different entities, and the system has to figure out the correct path or sequence of relationships to get the answer.
Like our Stanford professor example.
Exactly. Many professors at Stanford, many Alzheimer's researchers, finding the one who fits both requires navigating this complex web of relationships, not just following one obvious hop.
Okay, so current RE struggles with connecting knowledge across docs. Inefficient for multi-step questions, especially these pathfinding ones. Enter HIPPO. How does its architecture mimic the human memory system to tackle this?
This is where the biological inspiration really comes alive. So HIPPO models the neocortex's processing ability by using an LLM, their artificial neocortex, to transform a bunch of documents into what they call a schemaless knowledge graph.
A knowledge graph. Okay.
Think of this knowledge graph as their artificial hippocampal index. Instead of encoding whole passages into dense, isolated chunks, the LLM extracts key pieces of discrete noun phrases and the relationships between them.
Ah, so more fine-grained, like the pattern separation idea.
Exactly. The concepts, the noun phrases, become nodes in the graph. The relationships the LLM extracts from the text, those are the edges connecting the nodes. They use a process called open information extraction, or OpenIE, for
Like nodes and edges. And what about the parahippocampal regions, the connectors?
Right. To mimic their role, HIPPO uses retrieval encoders. These encoders add extra connections, extra edges between noun phrases in the graph that are similar in meaning but maybe not identical, based on semantic similarity.
So linking synonyms or related concepts.
Yeah, this helps with that pattern completion ability we talked about. If you have a partial match, it helps retrieve the full picture by leveraging these extra connections.
That sounds fundamentally different from how standard RAG organizes info. So what happens when you actually want to retrieve something? Answer a question.
Okay, so the online retrieval phase mirrors memory retrieval. First, the LLM extracts the important named entities from your question, the query named entities.
The key terms in my query.
Right. Then these entities get linked to the corresponding nodes in the knowledge graph based on similarity, again, using those retrieval encoders. These linked nodes become the query nodes. The starting points, the cues.
So like activating the relevant concepts in the knowledge graph.
Precisely. And this is where the hippocampus part really kicks in. To mimic how our hippocampus efficiently searches its network, they use the personalized PageRank algorithm, PPR.
PageRank like Google uses for web pages, but personalized.
Exactly. It's a variation. The crucial difference is PPR distributes importance or probability across the graph, starting only from a specific set of source nodes, in this case, our query nodes.
Okay, so it's like lighting up those initial query nodes and seeing which other related nodes get activated or get a higher score within the graph's network.
That's a great way to think about it. PPR lets HIPPO efficiently explore the relationship network, identify relevant subgraphs, and effectively perform multi-hop reasoning all in a single retrieval step.
A single step, not iterative.
Not iterative for the core reasoning, no. It finds those indirect connections standard methods often miss in one go. Then finally, just like the hippocampus signal helps retrieve info from the neocortex, HIPPO aggregates the output probabilities from PPR over the original documents.
Ah, linking back to the source text.
Right. This gives each source document a relevant score, which is then used to rank them for retrieval.
Wow. So instead of iterative searches through individual docs, it's a single pass.
Yeah.
Activate concepts, propagate relevance through this interconnected knowledge graph, then rank the source docs.
You got it. The PPR enables that single-step integration across multiple documents. The paper also introduces this neat concept called node specificity.
Mode specificity.
They call it a biologically plausible alternative to IDF, inverse document frequency, which is common in traditional search.
Okay. How does node specificity work here?
It's simple, actually, calculated based on how many original documents a particular noun phrase, a node, appears in.
So a rarer concept gets a higher score.
Exactly. A more specific concept appearing in fewer documents has higher node specificity. This score is used to weight the query nodes before running PPR. The idea, like the symbol sizes in their figure 2 show, is that more specific starting points can lead to more focused, relevant retrieval.
That's really clever, drawing such direct parallels to our memory system. Okay, the crucial question. How well does it actually work compared to existing methods?
The results in the paper are pretty compelling, yeah. They tested HIPPO against several strong baseline ARG methods, BM25, Retrieval, Colbert TV2, others on tough multi-hop QA benchmarks like music, and 2 wiki multi-hop QA. Looking at Table 2, HIPPO significantly outperforms them. We're talking improvements of up to 20% on some key metrics.
20%. That's a substantial leap in this field. What about other data sets? Maybe less complex ones.
They also tested it on hotpot QA, which is generally seen as a bit easier for multi-hop QA. There, HIPPO performed comparably to the best baselines.
Interesting. So its real strength shines on the harder problems needing that cross-source integration.
That seems to be the case, yeah.
Okay, accuracy is one thing.
Yeah.
What about efficiency? We talked about iterative methods being slow and costly.
Right, and this is another big win for HIPPO. Table 17 in the paper shows its online retrieval. The part that happens when you ask a question is way cheaper and faster than iterative methods like IRQT.
How much faster?
They report it being 10 to 30 times less expensive and 6 to 13 times faster, while getting similar or even better accuracy. That single-step multi-hop capability makes a huge practical difference.
Wow, 10 to 30 times cheaper. That could be massive for real-world deployment. The paper also mentions combining HIPPO with IRQT. What happens then?
Interestingly, yeah, they found that combining them actually led to further substantial gains across all 3 data sets. Table 3 shows this. It suggests they might be complementary, maybe tackling different parts of the retrieval challenge.
Okay. So HIPPO's core strength seems to be this single-step multi-hop retrieval. They even introduce an all-recall metric. What does that measure?
Yes, all recall. Table 6 shows this. It measures how often the system successfully retrieves all the necessary supporting info needed to fully answer the question. Not just one piece, but everything.
And how did HIPPO do there?
Even bigger performance gains compared to baselines like Colbert TV2. It really highlights HIPPO's ability to not just find some relevant stuff, but to identify the complete set of evidence through its graph and multi-hop reasoning.
The paper has some great examples in Table 7 and Figures 3 to 5. The Alejandra's birthplace one seems to really show it following a chain of relationships.
Exactly. In that case, Alejandra's birthplace, Villa de Shira, isn't directly in the main passage about him. But because HIPPO built the graph, it knows Alejandra was born there, so it correctly identifies the Villa de Shira passage as important when asked about his origins.
Which a standard method might miss entirely.
Very likely, yeah. It
Yeah.
misses that indirect but crucial link.
And then there's the Stanford professor in Alzheimer's example again,
Mhm.
the pathfinding one. How does HIPPO nail that tricky case?
Right, that's tough because there isn't one obvious link. Lots of Stanford profs, lots of Alzheimer's researchers, and iterative search could easily get lost down irrelevant paths.
Get bogged down.
Yeah. But HIPPORAG's graph structure lets it associate those separate pieces of information. It can identify Professor Thomas as relevant to both Stanford professor and Alzheimer's research and pull his passages, even when other methods like Colbert TV2 and IRCOT struggle. They even detail how they carefully built these tough questions in Appendix E.
And Table 10 gives more pathfinding examples, right? Finding a book via author details, a film via director genre links, a drug via mechanism disease. It really seems to excel at these complex reasoning tasks.
It certainly looks that way, and another important advantage they point out is continuous knowledge integration.
Adding new information over time.
Right. Methods that rely on summarizing often have to redo the whole summary process when new data comes in. HIPPORAG, though, can just add new nodes and edges to its existing graph.
Much more efficient and scalable for long-term learning.
Oh.
Okay, so it performs really well, but why? What
Yep.
makes it work so well? The paper dissects this.
Yeah, one crucial thing was the LLM used for that initial open information extraction, building the graph. They compared using GPT 3.5 with a dedicated OpenE model called Rebel, and also different sizes of Llama 3.1, and the LLM choice mattered. Big time. Table 5 shows using Rebel caused a noticeable performance drop. GPT 3.5 extracted roughly twice as many triples those subject-verb-object facts as Rebel. It suggests the LLM's broader understanding and flexibility in finding more concepts and relationships is really important.
So it's not just grabbing obvious named entities, but understanding the nuances between them.
Exactly. They even did a small evaluation on the quality of the extracted info using a framework called CARB. Found a positive correlation. Better OpenIE meant better retrieval. Interestingly, while Llama 3.1 models slightly underperformed GPT 3.5 here, all the LLMs were way better than Rebel.
Okay, so a good LM for indexing is key. What about the personalized PageRank algorithm itself? How critical is PPR?
They tested that too, looking at simpler ways to use the graph, Table 5 again, just multiplying query node importance by node specificity, or only looking at immediate neighbors. Neither performed nearly as well as full PPR.
So PPR's ability to really explore the network, follow chains of connections across multiple steps, that's crucial.
Seems to be a key driver of the strong results, yes.
So the winning formula seems to be powerful LLM building a rich, connected graph, plus sophisticated PPR navigating that graph efficiently. Makes sense.
Yeah.
But of course, no system's perfect. What are the limitations in future directions?
Right. They're quite open about that. The error analysis in Table 11 highlights a few things. One was limitations in named entity recognition, NER. Sometimes it didn't pull enough key info from the query to properly start the search in the graph.
The starting point wasn't quite right.
Yeah, and also errors from the OpenAI process itself, missing crucial relationships or messing up time-related info, like in Table 15.
They also mentioned a context trade-off. What's that about?
Well, because HIPPORAG focuses so much on individual entities and their direct links, it can sometimes miss broader contextual clues from the surrounding text in the original documents.
Okay.
Table 12 has an example. Colbert TV2, which looks more at surrounding context, correctly finds passages about famous Spanish navigators. HIPPORAG, focusing tightly on the specific entity Sergio Villanueva, who's actually a boxer, retrieves a different, though still relevant, passage.
So focusing too tightly on entities might mean missing the bigger picture sometimes.
That's the trade-off, yeah. To tackle this, they tried uncertainty ensembling. If the system isn't very confident about linking the query to graph entities like DEC, the similarity is low. It combines HIPPORAG scores with scores from traditional dense retrievers.
Hedging its bets, kind of.
Sort of, leveraging the strengths of both approaches, entity-focused graph and context-aware dense methods. Tables 13 and 14 show this helped, especially on music and hotpot QA.
What about dealing with really long documents and the initial setup cost?
Good points. They did notice GPT 3.5 Turbo's OpenAI performance dipped a bit on longer passages, Table 16, likely just harder to parse complex sentences. And yes, the initial offline indexing, building that graph with a powerful LLM, Table 18 shows it can take more time and compute cost upfront compared to methods like IRPOT.
But potentially cheaper long-term.
Well, and crucially, they point out that using open source LLMs like Llama 3.1 for indexing could significantly cut those upfront costs, makes it more feasible.
So future work seems clear. Fine-tuning NER and OpenEye, maybe exploring other graph algorithms, handling long docs better, scaling up.
Exactly.
They also briefly touch on something huge right now. Massive context windows in LLMs. Could those just make methods like HIPPO obsolete eventually?
That's the million-dollar question, isn't it? Context windows are getting enormous. But the paper rightly points out just relying on huge context for effective long-term memory and complex reasoning still faces big challenges.
Engineering hurdles. Performance issues.
Both. And current long context LLMs haven't really proven they can perfectly use info across, say, millions of tokens reliably yet. So for the foreseeable future, methods like HIPPO offering more structured, efficient knowledge management, they're likely to remain very valuable.
Before we wrap up, how does HIPPO relate to other graph-based approaches out there?
They position it as distinct because it builds its knowledge graph from scratch using LLMs and then does unsupervised multi-hop retrieval. Some older methods needed pre-existing graphs like web links or needed supervised training to learn how to navigate.
So more self-contained and adaptable.
That seems to be the idea. They frame HIPPO as a strong example of the synergy between LLMs and knowledge graphs for better art. It's a growing research area.
This has been incredibly insightful. A real deep dive into HIPPO and its brain-inspired approach. So, to summarize, what are the key takeaways for listeners?
I'd say, 1, it's innovative, neurobiologically inspired design. 2, significant performance boosts on complex multi-hop questions, especially for integrating knowledge across sources and pathfinding. 3, major efficiency gains faster and cheaper online retrieval. And 4, that ability to continuously integrate new knowledge into the graph. It's a really compelling approach to long-term memory for LLMs.
It really does seem promising for tackling current ARG limitations.
Yeah.
And it leaves us with a big thought, doesn't it? Could this kind of neuro-inspired approach, mimicking how our brains learn and connect info, be a key step towards more human-like understanding and reasoning in AI?
Moving beyond just pattern matching.
Yeah, towards genuine knowledge synthesis and application. It's definitely something to ponder how this might impact different fields. It's a super active area, clearly lots more to come.
Absolutely. It's an exciting time with potential to really change how AI uses knowledge.
Well, thank you so much for breaking this down with me today.
Yeah.
And thanks to everyone listening for joining us on this deep dive.